Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Fresnel diffraction pattern of straight edges. Let's begin. Let us take a straight and sharp edge xy placed at a distance x from that of sources. The sources which is placed at a distance a from that of sources. S is the light source of monochromatic light source having the wavelength lambda. Here we place a screen. Which is at a distance x from that of obstacle or straight edge xy. From that of sources, there are some wave fronts. Let the wave front incident on that of straight edge xy named as AB. The ray of light passes at that of straight edge which meet that of screen at point O. Here x that refer as the pole of the wavefront, that one is the pole of wavefront, with respect to the point O, with respect to O. And that screen which is placed perpendicular to that of plane of paper. Let we prefer a point P on that of screen which is at a distance of small y from the center of that of screen O. Here we have to observe what will be the intensity at point P when we place a straight edge in front of that monochromatic source of light. Here these portions are said to be the geometrical illuminated region these region the geometrical illuminated region. And this portion and the geometrical shadow region, geometrical shadow region. As per the geometrical optics, shadow of that of straight edge begins sharply at point O in the downward direction with minimum intensity below that point O and uniform maximum intensity above the point O. But experimentally we observe that some illumination is still observed even in the region of that geometrical shadow. Here we observe some illumination. Some illumination is still observed even in the region of the geometrical shadow. In other words, we can say we observe that there will be not a complete darkness below O. That is not a complete darkness below O. And the intensity diminishes continuously and quickly as we move into that of geometrical shadow until there will be no such complete darkness is observed. Rather, the intensity diminishes continuously and quickly as we move into the geometrical shadow until complete darkness we observe. that is zero intensity. Is observed at a short distance below. So, what we observe experimentally? Some illumination is still observed even in that region of geometrical shadow. In that of geometrical shadow, we observe some illumination. What type of illumination that one is? That is not a complete darkness below that point O, or the intensity diminishes continuously and quickly as we move into that of a geometrical shadow until complete darkness is obtained. What we call that is zero intensity is observed at a short distance below that geometrical shadow region. Next, above the point O, what we say that is the geometrical illuminated region. What happened in that of geometrical illuminated region? The intensity in that of region just at point O is not uniform. It keeps on increasing as we move away from that of point O, and there appears alternate bright and dark bands of unequal widths and varying intensity above that of point O. What we observe experimentally, above the point O, the intensity in the region just at point O is not uniform. What type of intensity it will be? It keeps on increasing as we move away from the point O. There appears alternate bright and dark bands of unequal widths and of varying intensity. The intensity varies. The intensity in the region just at point O is not uniform. It keeps on increasing as we move away from that of point O, and there appears alternate bright and dark bands of unequal widths and of varying intensity. These 2 points we observe experimentally in case of diffraction of a straight edge. The phenomenon is basically named as diffraction. How Fresnel explained that type of diffraction at straight edge by using his assumptions. The concept of Fresnel's half period zones, with the help of Fresnel's half period zones, he can explain the diffraction pattern, the phenomenon of diffraction at straight edge, and what type of diffraction pattern we observe on that of screen. Analytically, we show it. Analytically, the intensity at the point at the point P on the screen. What should be the intensity at point P? That point P on that of screen, that depends upon what are the number of half period zones, found in that of region from point X to point P. Inside these regions, what be the number of half period zones we found, according to which we decide what will be the intensity at point P due to that particular wavefront. Depend upon this definition the number of half period zones, found in the region from point X to point P that can be calculated, and what be the path difference in between these two rays. So, the path difference, therefore, the path difference delta between the two optical rays reaching at point P is given by delta is equal to xp minus qp. So, the path difference here xp minus qp. What will be the number of half period zones inside these regions due to that particular wavefront? Decide what will be the intensity at point P. So, the path difference in between these two rays, we calculate xp minus qp. The value of xp in that particular triangle XPO, xp is equal to that square plus this square and its square root. So, x square plus y square is under root. X square plus y square under root minus qp. Qp is equal to sp minus sq. Sp minus sq, which is equal to x square plus y square to the power half minus sp. The value of sp, look at that particular triangle SPO. that one with the hypotenuse, this one is base, that one is the perpendicular. So that square plus this square is equal to the square of that one. That square is equal to a plus x whole square. This square, that is plus y square, is equal to the square of that hypotenuse. In place of SP, we write that is a plus x square plus y square, its under root, minus SQ. SQ is nearly equal to the distance A, since we consider the paraxial rays, means the angle is very small, that is A, as SQ nearly equal to A. Taking x square as common, we have x square 1 plus y square by x square, its under root, minus, here we take common as a plus x as common. Inside that of bracket we have, okay, a plus x square as common. We have 1 plus y square divided by a plus x square to the power half minus a. Now under root of x square, that is x 1 plus y square divided by x square to the power half minus its under root, a plus x square under root, that is a plus x 1 plus y square divided by a plus x square minus a. Now we evaluate these terms by using binomial theorem. Applying binomial theorem, using binomial theorem, 1 plus x to the power n is equal to 1 plus nx plus dot dot dot, neglecting the higher powers, which is equal to the path difference delta is equal to x 1 plus its binomial expansion y square divided by 2x square minus a plus x its binomial expansion 1 plus y square divided by 2 a plus x square minus a. Now simplifying, we have x plus y square divided by 2x minus 1 plus x is multiplied here minus 1 plus x minus y square divided by 2 a plus x minus minus plus a, here x plus x minus a plus a, so these terms are cancelled out. We have y square divided by 2x minus y square divided by 2 a plus x. Taking the LCM, 2x a plus x, we have y square as a plus y square as a plus x minus y square into x. Taking y square as common, the numerator side, 1 plus x minus x divided by 2x a plus x, or the path difference delta is equal to y square a divided by x is cancel out, y square a divided by 2x into a plus x. That will be the expression for path difference. Now, the condition for maximum intensity and the condition for minimum intensity we have to calculate. For maximum intensity, the path difference should be integral multiple of lambda by 2. For maxima, we know that the path difference delta should be odd integral multiple of lambda by 2, that is delta is equal to 2n plus 1 lambda by 2, or for nth term the path difference is written as y n square a divided by 2x a plus x, which is equal to 2n plus 1 lambda by 2, or yn is equal to 2n plus 1 a plus x x lambda divided by a, its under root. Look at that expression, that is yn is directly proportional to 2n plus 1 under root, where n is any integer having the value 0, 1, 2, 3, etc. Hence the distance of maximas, from point O are proportional to the square root of or natural numbers, that is 2n plus 1 under root. For maximum condition, we have the distance of maximas from O are proportional to the square root of all numbers. That with the expression we clarify yn is directly proportional to under root of 2n plus 1. Next, for minimum condition, minimum intensity, for minima we know that the path reference should be integral multiple of lambda. For minima, the path reference delta should be integral multiple of lambda, that is delta is equal to n lambda. For nth term we say delta is equal to yn square a divided by 2x a plus x is equal to n lambda, or yn is equal to 2n a plus x lambda divided by a under root. It is clear that yn is directly proportional to the under root of 2n, means the distances of the points where we found the minimas which are the even square root, which is proportional to the even square root. Hence we write it, hence the distance of minimas, the distances of minimas from central point O are proportional to the square root of even natural numbers. The square root of even natural numbers. That is under root of 2n. The condition for minima, here we obtain the distances of minimas from the central point O are proportional to the square root of even natural number, that is under root n. From that of particular concept, we say the intensity in the region above the point O on that of screen is not constant and changes, since the distance yn is proportional to the under root of 2n plus 1 for maximum condition and proportional to the under root of n for minima condition. Hence, with the increase of n, the bands gets closer and their width goes on decreasing as we move away from that point O. So, here if we draw a graph of intensity distribution, we found here, we plot a graph as intensity in x axis, in y axis, intensity along y axis and distance in x axis, distance from point O towards P in x axis, you observe in that of shadow region at first intensity and after that it will be decreasing like this manner. These are the maximas. Here are the maximas and these points are minimas. After that we have uniform illumination. Here we obtain uniform illumination. Look at that particular figure for that of straight edge and compare that intensity pattern distribution. In that of shadow region, there will be some kind of illumination, the intensity increases and gradually decreases, having the non-uniform width. Why there we observe some illumination? Because due to the concept given by Fresnel, according to his Fresnel's half period zone are that of geometrical shadow region. If we take that of wave front, there will be some contribution of this part. Due to the contribution of this part, we have some kind of half period zones. So, the intensity of these half period zones at a point which is situated in that of geometrical shadow region creates some kind of illumination. So, that type of interference pattern, that type of diffraction pattern we observe on that of screen in case of a straight edge. So, with the help of this video lecture, you understand Fresnel diffraction pattern of a straight edge. Experimentally, we conclude these 2 points. Analytically, we show how the results of experimental value we found out. Calculating the path difference and the condition for maximum intensity and the condition for minimum intensity, and graphically show the intensity distribution due to the diffraction pattern we observe on the screen for a straight edge. So, with this useful and informative notes, let me wind up this session. Thank you.